So today it's a pleasure to have our very own Raymond Co. He just moved from a postdoc at University of Michigan. So welcome Raymond, and he'll be telling us about new roles of the QCD Axion in dark matter and baryogenesis. So take it over.
Thanks a lot. Yeah, so I just recently moved from a code M to a coder M, and you guys have hired both new people from M to a coder M. I'm referring to Jen, who's going to come soon. So today I'm going to share a little bit about what I've been working on the past year or two, about how the new dynamics of the QCD axion in the early universe can lead to a completely new origin of dark matter and baryogenesis. So before I start, I just want to share something interesting that happened today in the history of science. So Ehrenfest, known for his theorem about the relation between expectation value of variables in quantum mechanics, unfortunately passed away on this day 87 years ago. All right, so the structure of the talk today is that I want to tell you a little bit about the understanding of misalignment mechanism. And I will tell you that the usual understanding of misalignment mechanism arises from some specific initial condition in the potential. And there are a lot more possibilities where you can start in the potential, especially considering the dynamics during inflation and after inflation. So I will start the talk with a review of the conventional misalignment mechanism, which is relevant for the case if the QCD axion is the dark matter that we observe today. Then I would focus my talk on the initial condition and label this 2, which means that instead of coming from the bottom of the potential, we could start from the top of the potential. And this leads to a new origin of axion dark matter, and also different cases for the baryon asymmetry production to explain the observed cosmological axis of matter over antimatter, meaning that why do we only see matter when we look out in the sky, and very little antimatter. So the first part is the review. So now, before we talk about the misalignment mechanism, I just want to define what an QCD axion is and what is the potential that I was referring to. To start, I want to look at the neutron EDM, the electron dipole moment. If you just do a very naive estimate of the size of the neutron EDM, you will find that it is the charge times the separation, as we have learned in introductory physics courses. And this very rough estimate tells you that it has to be around 10 to the minus 13 E times centimeter. But if you do a more sophisticated calculation with quantum field theory, you'll find that this depends on the coupling called theta bar, which is the coupling in front of the gluon field, GG2. And in terms of this theta bar parameter, the neutron EDM is as big as 10 to the minus 16 E times m. And when people go out and do the experiment, they found that the upper limit currently is 3 times 10 to the minus 26, which means that we have a parameter in the theory that's dimensionless, and it is less than 10 to the minus 10. We don't know whether that's exactly 0, but we know it's exceedingly small. The big question is, why is there such a parameter whose term is obeying all symmetries of the theory? And we normally would expect it to be order 1, but in this case, it is extremely small. So that's the question of the strong CP problem. How do we explain this smallness of the parameter? So the idea is to promote this theta bar parameter into a dynamical field called the axion. And this FA, you can think of it as some higher dimension operator suppression scale, the decay constant of the axion. When you have the axion coupled to the gluon, the QCD effects generate a potential for the axion. In that case, the potential will actually drive the axion to a field value that exactly cancels the bare theta bar contribution, the constant, meaning that the potential of the axion would set the axion to a point such that the overall theta effective parameter is 0. So this is what we say the axion dynamically solve the strong CP problem. And if we want to understand the axion from a bigger picture, then let's zoom out. It is what axion is. It is a Nambu-Goldstone boson from the UN symmetry breaking. And the symmetry we're talking about is the Peccei-Quinn symmetry, which is the shift symmetry in this complex field in the angular direction. So the angular direction is the axial, and the radial direction, we don't have a specific name for it in the non-supersymmetric case. But in supersymmetry, often people call it the saxion. So even though throughout the talk, I don't always evoke supersymmetry in my specific models, but I'm just going to refer them as saxions for convenience. So in this case, if you write the complex field as the radial direction and the angular direction, then the radial direction is called the saxion, the angular direction is the axial. And the axion would be massless if the temperature is still above the QCD confinement scale, because the QCD effects have not kicked in yet. But when the temperature is lower than confinement scale, then through the coupling between the axion and gluons, a mass for the axion starts to develop through the QCD phase transition. And at low temperature, it is given by a formula that only depends on the decay constant. So for a QCD axion, you can imagine the theory just parameterized by one parameter, the decay constant. And this decay constant is nothing but the vacuum expectation value, the radial mode the saxion would obtain at 0 temperature. So it is the radial mode that sets the decay constant. And for specific models, we need to have more than this complex field. So for example, we have the KSVZ model that you know very well that involves the heavy quarks charge under the Peccei-Quinn symmetry, or the DFSZ model where you have additional Higgs doublet charge under the Peccei-Quinn symmetry. So this is how we view the axion and the radial mode of the PQ breaking field in this talk. So first, let me review misalignment mechanism. Now I'm focusing on the angular direction. This angular direction gets the potential from the QCD effect, and it is a cosine potential along the minimum of this wine bottle potential. And I'm now focusing on only this dimension, this axion direction. So this is the equation motion of the axion. Hubble rate is here, and this is the axion mass. This is nothing but a simple harmonic oscillator. Hubble can be thought of as the friction term. And you may have heard this story a lot, but this is actually important for the new production mechanism I'm going to discuss in a bit. So the way to understand the solution of this equation motion is that when the universe is still very young, when the Hubble rate is still very large compared to the axion mass, especially when the axion mass is vanishing at high temperature, then the axion field value is a constant. That means the energy density of the axion is a constant. So that's what we say the field is frozen until a later time, which is when the Hubble rate drops below the axion mass shortly after the QCD phase transition. Then the solution of this equation is that the field would start to redshift. R is the scale factor of the universe. So the field starts to oscillate, but the amplitude of the field redshifts, meaning that the energy density of the axion field also decreases because of redshift of the universe. And the energy density redshifts as R to the -3. And this is exactly what we expect for matter, because you have the matter energy density, which involves the division by volume and volume expanding. So this is known since the 80s. So if I carefully putting the numbers for the axion misalignment mechanism, you will find that the observed dark matter boundness 0.11 is explained if I assume an order 1 misalignment angle from the minimum of the cosine potential, if I take FA to be of order 5 × 10⁻11 GeV. So this is the prediction from the misalignment mechanism if you assume QCD axion as the dark matter candidate. So that means if you're sitting at 10 to 12, then this only involves order 1 theta. But if you want to go to very small FA, then you have to make sure this theta is as big as possible, which is pi. That means you're at the hilltop. And there's an additional factor F. That's called an harmonicity factor. It tells you that if you're extremely close to the hilltop, then the onset of oscillation condition is slightly modified because you're almost at a flat spot. So it almost doesn't oscillate. So the oscillation is delayed, and that means you have an enhancement of the abundance. So you can go to small FA, but you just have to be extremely, extremely close to the hilltop. In the other direction, if you want to go to very large FA, then that means you want to make theta as small as possible. Then you will have to explain why, if it is a random initial condition, why would you start at the minimum at a point that's so close to the minimum? Remember that at high temperature, this potential is absent, so it's just a flat line. So the axion should be sitting at the random place until the QCD phase transition occurs. So that also requires fine-tuning of angle to a very small value. So this is the limitation of the misalignment mechanism. So in this talk, I'm going to focus on a different initial condition. Instead of assuming that the radial mode is not doing anything, we're assuming that the radial mode starts with a large field volume. And there are still two possibilities, that you can oscillate in the radial direction, or you can have some angular momentum in this wine bottle potential. And I'm going to focus on two today, even though one is also very interesting.
So Raymond,
yes.
a question here. So, and you're also assuming that the quality problem is solved in the sense that you don't have any higher dimension operators which explicitly break the symmetry and tilt the potential, right?
Almost. So I do assume that the higher dimension operators do not spoil the solution of the QCD of the strong CP problem. So that means the dimension has to be high enough. But in this talk, I actually have to have the presence of the higher dimension operators to initiate the cake, so that I have the angular direction. This is what I would.
So you'll bring in higher dimension operators at some point.
Yes, yes. So the higher dimension operator that you're referring to is exactly what's causing the wiggles in this wine bottle potential. If I have no higher dimension operator, this potential will be cylindrically symmetric all the way to large field value. But as you can see, at large field value, you start to have wiggles because of the higher dimension operator. And that's the key ingredient of our discussion.
Okay.
Yeah.
But the symmetry is broken originally in QCD, right? U1 symmetry is anomalous, right? So this is sufficient for appearance of non-zero mass, right? So it's not like having exact symmetry because the symmetry is still broken, you know, in a special way. So what Tony is asking, I'm not sure whether you're referring to something which beyond QCD, right? Because in QCD you already has a breaking of U1.
Yes. Yeah. So if you look at, let me see if I can go back to that. Yeah. So there are two contributions of the U1 break, and one is, as you say, the QCD effect, which is still there at high temperature, but it's just very, very, very small. So that's one effect. And Tony, I think, was asking higher dimension operator, which would be present at all temperatures. But since they're at higher operators, they are only effective if the field value in the radial direction is large enough. Because when the radial direction is small, then you have the Saxon field divided by the higher dimension or the suppression scale to a very high power. I will go into some details in one slide or two. Yeah, in 2 slides. Okay, so let me just talk about what we're considering today again. So this is on the left. This is what has been done in the literature. There are a few different ways you can initiate the dynamics of the PQ breaking field, either at the minimum or at the origin, start to oscillate, or at a large field value and start to oscillate. What we're saying today is that they not only can start from a large field value, but you can also have an angular motion when the oscillation occurs, which means that instead of radial oscillation, you have some spiral motion with both the radial oscillation and the angular rotation. So I have 2 things that I need to explain to you for this dynamics. One, why do we start with a very large field value in the potential? Why don't we start from the origin or the minimum? There's one way to, there are a couple of ways to understand it. You can understand it as the following. If the radial mode is light enough, meaning that the mass is less than Hubble, then it doesn't oscillate during inflation. So it would not be relaxed to the minimum. But again, why does it start from a large field value instead of some other one number from the decay constant? It is possible that it is just an initial condition. We don't know why it starts from there. It just turns out to be there. That's one possibility. But another possibility is that this radial mode couples to the inflaton. So that inflaton actually gives a Hubble-induced mass to the radial mode of the PQ breaking field. And that Hubble-induced mass can come in with a positive or negative sign. If this were negative, then the Hubble-induced mass would drive the PQ breaking field to a very large field volume. So this is the negative mass caused by the inflaton, for example. And this runaway direction would be stabilized by a higher dimension operator. So that means during inflation, you would have a negative mass that drives you to a very large field value, as large as, for example, close to the cutoff scale of the theory. So that would be one dynamical reason why the axion can start from a very large field value. So the second thing that I need to explain to you is why does it have an angular motion? Why does it get a kick in the angular direction? And this is, I think, exactly what Tony was referring to. You do have higher dimension operator that is not just on the radial direction, but it cares about the angular direction in this, for example, form, p to the n plus the Hermitian conjugate. So there's a cosine function when you expand it in the radial mode and the angular direction. So that means this contribution does give an axion mass. And that's why the axion potential or the potential in the axion direction becomes wiggly. And this is only happening at large field value, because otherwise, if you're taking the vacuum FA divided by this cutoff scale, let's say Planck scale or close to the Planck scale, to some power n, if n is large, normally of order 9 or 10, then this ratio to the 10th power is small, very small, so small that it doesn't give an axion mass larger than the contribution from the QCD effect. In that case, then the solution to the strong CB problem is of high quality, meaning that you don't have other explicit breaking that is important. But what I'm trying to argue here is not a quality problem, but that if you start out in a very large field value in the radial direction, it is possible that this higher dimension operator usually we neglect because of a large ratio, a small ratio between P and M. This ratio may not be small in the early universe. If we start out with a large P, then P over M can be order 1, and order 1 to the 10th power may not be negligible. That's the claim. So where do these higher dimension operators come from? For example, as we know, there is the axion quality problem. Even if you want to use the QCD axion to solve the strong CB problem, you still expect these higher dimension operators because, for example, the conjecture from quantum gravity is that quantum gravity does not respect a global U1 symmetry, which means that there's always a higher dimension operator, for example, suppressed by the Planck scale that breaks the PQ symmetry. So that's one possibility. Another possibility is that you can understand PQ as an accidental symmetry. In that case, then the incident may not be exact in the sense that you still have some higher dimension operators. So in all of these cases, we're arguing that the higher dimension operators are generic and they can be very important in the dynamics of the QCD axion if the axion starts from a large field value, which is also possible in the consideration. And this large field value is similar to what people have discussed about the moduli problem with light fields. And everything I talk about here, the initiation of the rotation, is analogous to the dynamics in F-like-Dime baryogenesis. The main difference is that instead of talking about the QCD axion or the PQ breaking field, they are talking about the scalar partner of the baryons of the quarks or the leptons. So for example, it's quarks and leptons. Those scalar fields can do exactly this kind of rotational motion with U1B breaking terms. So the baryon number validating terms instead of the PQ breaking terms. So so we're borrowing this initial condition or initial dynamics from FLECT, and we applied it to the QCD Axion scenario.
So Raymond, so just to clarify, so then you're basically going to add a higher dimension operator that's consistent with solving the Axion quality problem. But then you're saying that that particular higher dimension operator is going to be the source for this angular motion.
Exactly.
Okay.
Yep. And the main point here is that why does it become important when we say we have high quality? The reason is that we start with a large P.
Excuse me, what is the Axion quality problem? What's the Axion quality, what it is?
Oh, I see. So what it is that as we saw before, if we want to solve the strong CP problem, we want to dynamically drive the axion to the minimum of the potential. Let me see if I go back to this slide. Yeah. So we're claiming that there's a contribution from the QCD that drives the axion to the minimum.
Yes.
But this is assuming that there's no other contribution to the axion mass or potential.
Okay.
And if there's a higher dimension operator coming from, for example, quantum gravity, then in that case, this contribution could also have an axion mass. And if this contribution is too large, then it is driving axion to a minimum that may not be the minimum that preserves CP.
Okay.
Yeah, so any additional mass contribution to the axion, you have to be very careful. You have to make sure that it is smaller than the QCD contribution. Otherwise, you're driving it to a different field value that does not necessarily solve the CP problem.
Of course, because you introduced CP breaking operators explicitly, right?
Yeah.
Not for the anomaly, but explicitly, sure.
No, but not only CP breaking, but it's also U1 breaking.
Yeah, yeah, sure.
Because specific of QCD is that you are kind of technically not breaking U1, right? I mean, besides anomaly. But this additional part would be even breaking U1. So then the whole idea that it is symmetry becomes a little bit.
Yeah, of course. If you don't have U1 symmetry, then of course you don't push. You don't. You don't make effective theta equal to 0, of course.
Yeah. Of course. Unless there's any specific reason why the new minimum you're driving to happens to be aligned with the CP conserving minimum, but that requires additional mechanism.
No, it's not additional mechanism, because if you are just the only source of breaking U1, then theta drives effective theta goes to 0 anyway, because then this effective mass which produced would be contained in theta minus A. That's it, right? So theta plus A. So I mean, in this way, square. So in this way, minimum would be automatically at CP preserving.
Yeah.
If there is no other source.
Yeah, exactly. Yeah. That's what I mean as well.
Yeah.
Yep. Okay. So hopefully this gives you a reason, background knowledge of why rotation is worth considering, and it is possible. And to my opinion, that is very well motivated, considering that there's a vast literature on FTPI baryogenesis, and also a large literature on the axion quality problem.
Yeah, but for example, when you're saying it's quantum gravity, then it implies that quantum gravity breaking U1.
Yeah, that's the assumption.
Yeah.
Yep. Okay, so let's understand the rotation in a different way. So we now understand it from the picture. We want to also define something called a PQ charge. So you can think of it as a conserved quantity associated with the symmetry of the problem, which is the Noether theorem. In this case, we have a shift symmetry, and the conserved quantity in this case would be the angular momentum. And if you actually go about computing this conserved quantity due to the shift symmetry, you find that the formula for the conserved quantity number density is given by s squared theta dot. S again is the radius, theta dot is the angular velocity, which is nothing but what you have seen before, r squared omega. and that's the angular momentum. But in this case, the interpretation of the angular momentum is the axis of PQ charge, meaning that when the PQ breaking field rotates one way instead of the other, then you have more PQ charge in one side than the other. So the overall PQ charge will be positive or negative, depending on which way you turn. But the upshot is that you have a conserved quantity called the PQ charge due to the rotation. Well, it said my internet was unstable. Did you guys hear me?
I can hear you fine. At least I
Okay.
have.
Okay. All right. So the understanding about this picture is that the explicit PQ breaking, the wiggles in the potential, give the kick, which generate the PQ charge, the PQ asymmetry. But this PQ charge becomes conserved soon after the onset of the rotation, because the higher dimension operators become inefficient very quickly when the radius of the PQ breaking field drops just a little bit due to the high power of the higher dimension operator. And the following discussion of the talk is how we deal with this PQ charge. But let me just give you a sense of what the dynamics looks like in the cosmological evolution. At first, you have very quick rotation and also oscillation in the radial direction, because you may not be able to generate a perfect circular motion. In that case, then you have elliptical motion, which means that you have energy not only stored in the rotation, but also in the radial oscillation. And the radial oscillation, the saxion, would cause cosmological problem, because first we assume very light saxion, so they may decay very late. If they don't decay at all, then they may overclose the energy density of the universe. So we want to thermalize the radial mode.
What do you call light? Is the radial mode?
For example,
Yeah.
So I'm thinking, for example, GeV to TeV.
It's light,
and I call it light because light compared to the FA, the decay constant.
Okay.
Because we expect the radial mode to normally, if you don't think about supersymmetry, with order 1 quartic coupling in the quartic potential, you assume the axion to the saxion to be as heavy as the decay constant. But we're taking something much smaller. But my light saxion is still much heavier than the axion itself.
Yes, so sorry. So I mean,
Yes.
I guess that you were saying that. So you're taking a quartic coupling, which is really tiny, then in the axion potential for P, right?
Yeah. So if you're assuming that there's no supersymmetry, then yes, then the quartic coupling has to be extremely small. But in supersymmetry, we could forbid the saxion mass and then generate it from SUSY breaking. So we forbid the saxion mass by the, for example, PQ charge assignment, and then you generate it from the soft breaking of the supersymmetry. In that case, then the saxion can be naturally at GeV or TeV. And in that case, then the potential itself is natural.
But if I take like the KSVZ potential, then the quartic coupling has to be like 10 to the minus 12. Is that right?
So KSVZ can be in supersymmetric or non-supersymmetric realization. In this non-supersymmetric realization, then I agree. So the quartic coupling, I think, would be the ratio between the saxion mass and decay constant squared, which would be, for example, 10 to the minus 18.
Right. Okay. Yeah.
Or or of that order. Yeah. So that is true for quartic potential, but for supersymmetric case, the potential itself can be made natural. Okay, and here I just want to show you the dynamics of what happens if I thermalize the radial mode, because we don't want to overclose the universe. We don't want to spoil the BBN calculation from late decays and so on. So when we thermalize the radial mode, instead of running in the elliptical motion at thermalization, what happens is that the radial mode energy density is depleted into the thermal bath. And now we're only left with the perfect circular motion, if you saw the video. And this perfect circular motion is still there, not being thermalized, because we have a conserved quantity. So this PQ charge is conserved. if you think about the thermalization processes that we consider, we don't violate the PQ charge. In that case, then the only thing can remove from this field dynamics is the energy that is not associated with the angular momentum. So to minimize the energy without changing the angular momentum, the most you can do is to extract energy from the radial oscillation, and you're only left with the angular motion. And this is what happens at the time of thermalization. And after thermalization, what happens is that this field continues to rotate in the circular motion, but the radius shrinks because of the redshift of the field, the redshift of the energy density. And that's again due to the cosmological expansion. So that's the dynamics that's very unusual compared to the oscillation case. Okay, so now I also want to explain to you that from this angular momentum understanding, how do we see that there's a very large angular speed at low temperature for what we will consider later. So this may be the reason why this direction of research has been overlooked. The reason may be that if you think about the angular momentum that we described, r squared omega, s squared theta dot, and that's a conserved quantity up to the volume expansion of the universe. So in the conventional case, where the Saxion takes the vacuum volume throughout the whole evolution of the universe, in that case, because n times r cubed should be a conserved total charge, so n always scales as r to the minus 3, with s being a constant. That means theta dot itself has to scale as r to the minus 3 for that scaling to be consistent. So that means the redshift of theta dot will be extremely fast if the radial mode is already at a minimum throughout the whole evolution. So whatever you generate during inflation in theta dot would be redshifting away until, by the time of, for example, QCD phase transition or the electroweak phase transition that we would talk about in the case of baryogenesis. So that's why this has no effect if you take S equal to FA. But
Raymond, I'm sorry, but it is implied that you are in the in the situation where U1 symmetry is maintained, it's not broken, or it's an equation where it even with the breaking of U1 due to anomaly.
Due to the QCD anomaly?
Yeah.
Yeah, I do assume that there's the breaking due to the QCD anomaly at temperatures below the QCD.
So you are neglecting this at this stage, right? Right. It's just for me to follow. So in this way, U1 symmetry is still kind of a good one. I mean,
yeah, that's right. And that's because I'm initiating this dynamics at a temperature much higher than the QCD phase transition. So at that time, you can assume that the QCD effect does not violate PQ's symmetry yet.
Okay, thanks.
Okay, thanks. Yeah, so now we're considering, instead of the case of S being FA the whole time, we're considering where S starts from a large field volume and then go through the motion that we described in terms of the elliptical motion and the circular motion. In that case, for example, for quartic theory, the radial direction square scales as r to the minus 2, and that would imply that theta dot scales as r to the minus 1, which is already slower than the conventional consideration. This is similar to where you put a coin in a bowl that you have seen in those malls where you can donate coins and you can see the rotation of the coin down the hole, and then you see that the coin will go faster and faster to the smaller and smaller velocity. That's exactly to smaller and smaller radius. And that's exactly the same idea, that you have a large angular momentum. When you shrink the radius, the angular velocity would go up, but in the expanding universe, it just cancels some of the redshifting. So this redshifts slower in the case of quartic. In the case of quadratic, it's even more dramatic. The radius square scales as r to the minus 3. That would imply that theta dot will actually be a constant. So the redshifting and the shrinking of the radius exactly cancel the effect of each other and leading up to a constant theta dot. So that means if you initiate some theta dot at high temperature, this theta dot would be the same theta dot until the radius shrinks down to the minimum. When the radius is FA, then it starts to redshift. So that's how we are able to preserve a much larger angular velocity than the conventional consideration. Okay, so now I want to start telling you about the application or the implication of this dynamics. First, I want to start with dark matter. So it is about the mechanism that we call kinetic misalignment. So the main idea is that what you have seen before in misalignment mechanism is that you have some field sitting at rest, waiting until Hubble dropping below the mass and it starts to oscillate. Instead of this picture, we're starting with the condition that it is not at rest, but coming with a very large kinetic energy. And this large kinetic energy would delay the usual onset of oscillation, because at the usual time of oscillation, when Hubble is comparable to the mass, the kinetic energy may be so large that it simply overcomes all the potential barriers. So it keeps running in the bottom of the one bottle potential. So here's the animation to show you what's happening. The blue dot is the conventional misalignment, and the red dot that you haven't seen is the kinetic misalignment. So at the time of oscillation, of the usual oscillation, the red dot is still coming. 1 second, you see that? Okay, here it is. So it's still coming with a very large kinetic energy, and it only starts to oscillate at low temperature because the kinetic energy has redshifted sufficiently that it does not have enough energy to overcome the potential barrier anymore. So you get trapped to one of the minima, along the minima of the potential. So this has the effect of delaying the onset of oscillation, and that means that you are enhancing the dark matter abundance. So to understand this again from the energy argument, because we're thinking about the QCD axion, the QCD axion at very high temperature has zero potential, essentially zero. And the potential energy starts to grow during the QCD phase transition. And the kinetic energy starts high because of the rotation and starts to redshift. And when these two curves meet, that's when the kinetic energy is not sufficient to overcome the barrier of the potential. And that's the point when you start oscillating along one of the trough instead of going over the potential. And another way to see the same thing is that you can see how theta evolves. So theta is running very quickly. So there's the large slope, but the slope is getting smaller and smaller. So eventually, when the slope is small enough, meaning the kinetic energy is not large enough, then you get trapped and you start to oscillate along the minimum of the potential. So this kinetic misalignment mechanism is able to explain dark matter with the observed abundance with decay constant as small as the astrophysical bound of 10 to the 8 GeV. And this YPQ is the Peccei-Quinn charge yield, which is the number density divided by the entropy density. But the key point here is that with UV parameters that can realize this YPQ, we're able to explain axion dark matter with a decay constant very small compared to the conventional misalignment mechanism, where you would need to require the misalignment angle to be extremely close to the hilltop. Okay, so that's one application for the rotation in terms of dark matter. And now I want to move on to the application to baryogenesis.
So Raymond, if I could ask a question, so what's the source of this initial kinetic energy? I mean, how is this is just something you assume during the universe?
Yeah, so this kinetic energy is nothing but the theta non-zero theta dot, right? And non-zero theta dot is coming from the rotation that we discussed.
I see.
So the idea is that the kinetic energy I was describing in the case of misalignment, kinetic misalignment, is the kinetic energy when you're running along the bottom of the wine bottle potential. But this kinetic energy of the axion is nothing but the rotation of this PQ breaking field, because the angular direction is the axion. So it is the rotation that we described that leads to a very high kinetic energy in the axion.
So basically the source of all this is the inflaton pushing the radial mode out to a scale which is significantly, well, it's larger than FA.
Yes. Yeah, and after that, then everything kind of evolves.
Everything then evolves. So that's where the initial energy comes from then.
Exactly. Initial energy was this very large potential energy coming from the inflaton dynamics. And then the angular energy is coming from the explicit breaking, where you get a kick at the onset of oscillation. Yeah, and that rotation would continue along the minimum of the potential, and that leads to this picture. So this line, this horizontal axis, is the angular direction of the PQ breaking field, which is along the minimum of the wine bottle. And this dot is representing the PQ breaking field that is at the minimum of the potential. So that's why I kind of suppress the radial direction and only focus on the angular direction.
But for you, the inflaton, it's just some particle that has that potential that you, with a high dimension operator, right? That's all it is for you at this point.
So the higher dimension operator does not have to come from the inflaton. For me, the inflaton is only playing this role. Let me.
Yeah, you had this mod P to the 2D, right? You just need that term.
Oh, I see. So that term does not have to come from the inflaton. This can just exist as a higher dimension operator. The inflaton plays a role in this term, in the term that generates the Hubble-induced mass. Yeah.
I see.
Yeah. So you don't have to have inflat. I guess you have to have
that, right? I mean, Raymond, that's what we did. Is we said that it was just the fluctuations in the scalar field that give you the large expectation value to start with. That's unavoidable. Right?
Yeah, yeah. So yeah, I guess there are two ways. Now you just mentioned the third way too.
Because the other one you can't avoid. So you can do other things. You could put this potential in, but the scalar field fluctuations that you get during inflation are unavoidable, right?
Yeah,
unless for some reason the axion has a huge mass to prevent it from drifting out to large field values.
Yeah, but I guess the difference may be that if you're using quantum fluctuation of scalar field during inflation, then the field excursion would be as large as the Hubble rate during inflation, right? And if you're using this,
much bigger than that, right? It has a maximum value of h to the 4th over m squared.
Yeah, that's true. If m is small enough, yes. Yeah. That is also, that's also one way to see it. Yeah, but it depends on whether the quantum fluctuation field excursion leads to a larger field value, or if I have this Hubble-induced mass that drives me to a larger field value. So either case is possible. Yeah. So, and we're not preferring one or the other. But that's a good point. That the field excursion during inflation may also put you at a very large radius. Yeah. But one main difference may, as you know, Keith, that if you're using quantum fluctuation during inflation, then there's isocurvature from dark matter and the baryon symmetry that may be a stronger constraint than if I dynamically drive it to a minimum.
Yeah, but again, you have no choice about those things, right? I mean, the quantum fluctuations are there, so it's you
yeah,
can't.
but I could have a larger or stronger Hubble-induced mass during
That you can do.
Yeah, in that case, then I dynamically fix it to a point instead of letting it fluctuate around.
Yeah, so then actually, how do you turn off the quantum fluctuations then, as Keith is pointing out, if you have this potential, right? Wouldn't it put you out even further?
So it depends on the two contributions, right? The quantum fluctuation can be as large as Keith said, hi to the 4th over m squared. But if I just think about this Hubble-induced mass, it would put me at the scale that is very close to the cutoff scale of the theory.
Oh, okay, yeah.
Here, right? If because of the high dimension d here. Let's say if d is 10, then if d is 10, then this could be the geometric mean could be very, very close to m. Right. In that case, then then the quantum fluctuation will be a small fluctuation from the m. Yeah, so either case is possible, but the constraint may be different. Okay, so now I want to apply this mechanism to the rotation. The first case is called axiogenesis, and it has the meaning of the QCD axion plus baryogenesis. That's why we call it axiogenesis. And it has received some popular science article coverage. And we're finding it very exciting because now we're claiming that the axion not only solves two problems, not only the QCD, the strong CP problem, but also dark matter, and now the baryon asymmetry of the universe. So the story goes like this. As we have said that the rotation corresponds to the PQ asymmetry, which is a charge density. And we know the QCD axion by definition has a strong coupling. And that strong interaction would involve a strong sphaleron process, which means that it is going to transfer this PQ asymmetry, this PQ charge, into the quark-chiral asymmetry. And this quark-chiral asymmetry will be further processed in the standard model by the electroweak sphaleron process. And after this second step, then now you're transferring this quark-chiral asymmetry into the baryon asymmetry. So this is how you think about where the baryon asymmetry is coming from. It is from the PQ asymmetry, and then both of these processes are existing in the standard model. And the key thing here is that because we're talking about QCD axion, so the strong sphaleron process is a guarantee, and the electroweak sphaleron process is always there. So this part we can also say is pretty much automatic, as long as we have the rotation to begin with. But if you're thinking about,
what do you mean by strong sphaleron? You mean that you are below the temperature of the QCD phase transition, and then at strong coupling. What is the strong sphaleron at strong coupling?
So I don't have to be in the I don't have to be below the strong the QCD phase transition. So this strong sphaleron occurs at temperatures higher than the QCD phase transition.
Okay.
Yeah, so the sphaleron process, because the PQ symmetry is anomalous under SQ3, that means the sphaleron process, which is the transition from one vacuum state to another vacuum state, would change the PQ number by a unit, and that would put the PQ asymmetry into more left-handed quarks than right-handed quarks. And that's what I mean by the quark-chiral asymmetry.
Well, it's a little bit misleading, because if your temperature is much higher than the QCD coupling, than the QCD scale, then of course you don't have this, the potential which kind of have maximum, minimum. Sphaleron is the height of the maximum, right? But above at high temperatures, you don't have maximum or minimum. All these different copies of the QCD vector, they are not separated by a barrier.
Yeah, they're not separated.
The barrier is very low, in fact, compared to the temperature. So you go far higher than the barrier.
Yeah, so that's exactly what allows us to do the transfer. If the temperature was lower than the potential barrier, that means you never transition between the minima.
Yeah, I understand. So I'm just noting that the word sphaleron is not quite appropriate for this situation,
I see.
Is it just the fluctuations that make GG dual correlator non-zero, right?
Yeah.
But you are talking about electroweak sphaleron. It's a different scale, right?
Yeah, electroweak are a different scale, sure.
And it is much larger scale, right? For electroweak.
Much larger than QCD scale. But this scale, where it's written strong sphaleron, is the temperature is still much higher. It's assumed to be much higher than the electroweak sphaleron. So it's not, strictly speaking, it has nothing to do with sphaleron, just tells you that the quarks, because of the axion is coupled to the gluons, there is certain, kind of, and the axion carries some, it moves, right? What is the rotational mode? Is that axion field grows, let's say, grows with time, and this gives you, or or in space. And this gives you some asymmetry between left-handed quarks and right-handed quarks. That's how I understand it. So
no, but it also involves leptons, right? Because it is above the scale, right? So
yeah, it also gives asymmetry to the leptons too. Sure.
Yes, yeah. So, but the leptons may not come directly from the PQ asymmetry. It can come from the reprocessing of the quark carrier symmetry.
Yeah.
Yes, yeah, that's possible. Yes. Okay. Yeah, so the other thing I was going to mention is that if we're not considering the QCD axion, then this red line is absent. In that case, then we're discussing, for example, axion-like particle. For an ALP, you can have the PQ symmetry anomalous under the SU2 symmetry. In that case, then you have electroweak sphaleron process, or the process that changed the PQ number and convert it into directly the baryon symmetry or to the quark carrier symmetry. So that's also possible, and I just didn't have the time today to discuss the ALP case. I'm still focusing on the QCD case. But even for the QCD case, this blue dashed line is still possible. It doesn't mean that we cannot have electroweak anomaly. All right, so now let's start looking to how we estimate the baryon symmetry from the rotation. So from the rotation, we know we're generating a non-zero theta dot. And this MB is the baryon number in equilibrium. If I assume everything is in thermal equilibrium, this CB is a model-dependent coefficient. This number 0.1 is coming from the first route where I go through the strong sphaleron processes. And this CW is coming from the blue dashed lines. If I do have the non-zero anomaly coefficient of the electroweak, then I could have an additional contribution. But the idea here is that the equilibrium value in the thermal bath is given by theta dot times T squared. T is the temperature. So this whole system remains in equilibrium value until the temperature of the electroweak phase transition. Because at that point, this electroweak processes would become out of equilibrium. So the transfer stops. So this baryon asymmetry would freeze out.
But at this high temperature, why it's B? It should be B plus L or B minus L, right? Because there leptons are involved. So I mean, I'm just trying to follow that you're implying that it is NB, but at this temperature, it's difficult to say whether it's at B or B plus L or B minus L.
Yeah. So technically speaking, it's B plus L. I'm kind of
it's what I'm wondering. Yeah, I see.
Yeah. So technically we're generating B plus L at this stage.
I see.
Okay. Yeah. I'm trying to simplify the notation or the discussion here. Yeah, but you're right. Okay. In that case, then I can finally estimate the baryon symmetry from this number density of the baryon divided by the entropy density of the baryon, the entropy density of the universe at the time or at the temperature of the electroweak phase transition. In that case, then it is related to the PQ charge asymmetry, but suppressed by this ratio, the electroweak temperature divided by the decay constant square. And this YB is the one that we want to match onto the experiment. The observation is that it is 10 to the minus 10 for the baryon asymmetry that we observe. So if I put in the, for example, electroweak phase transition temperature of 130, then you will see that I need a decay constant as low as 10 to the 8 GeV, and the yield of the PQ charge is as big as 500. And everything here looks just fine, but remember this number of 500 for FA of 10 to the 8 for a few slides. This is going to be important later. Because at this stage, we're only talking about the production of baryon symmetry. And earlier I told you that there's also application to dark matter. And remember at this stage, for axiogenesis, what we care is the rotation at the electroweak phase transition. But for kinetic misalignment, we care about temperatures below the QCD phase transition scale. So now the question is the rotation, the amount of rotation that we are requiring at the electroweak phase transition to explain the baryon symmetry, is it consistent with dark matter consideration at lower temperature? So between these two temperatures, what happens is that theta dot, the rotation, is redshifting, as we're already at the minimum of the potential. In that case, then we can redshift from this temperature to the oscillation temperature and see if we're overproducing or underproducing dark matter. And the bottom line here is that we're using the baryon symmetry to fix the rotational speed, or equivalently, we're fixing the yield, which is 500 that we need for FA of 10 to the 8 GeV. So now let's put everything together. If I'm assuming exactly this yield that I need for kinetic misalignment, then the dark matter abundance that we're seeing turns out to be 140 times the observed abundance of dark matter. And that means we're overproducing by a factor of 140. If this number was 1, I would totally call this axiogenesis miracle. But life is never what you expect, and it is just slightly too big, 140 times too big. Then you can say, okay, then we can play with the numbers. So let's say, what if we make FA smaller? As you know, there's a lower bound on FA from astrophysical constraints. So FA cannot be much smaller, cannot be smaller than 10 to the 8. Even though it used to exist a hadronic window where the supernova constraint is absent when FA is around 10 to the 6 GeV, and that would be perfect for our consideration. But it seems to me that this hadronic window has been ruled out recently. Another possibility is to raise the electroweak phase transition temperature by a factor of 10. And that would make not only the baryon symmetry consistent, but also dark matter. So that's one possibility. The other possibility is to have the CB parameter. And I didn't have time to talk about how we derive the CB parameter, but that tells you how efficient you transfer the charge. The way you can increase it is to have the electroweak anomaly to be very large. For example, a factor of 100, bigger than what we assume. And that would be possible if you're thinking about clockwork axion, where you have a large PQ charge for some of the fields. In that case, then the anomaly coefficient can be huge. And with all those possibilities, it is possible that we can make two considerations consistent. And that's the plot for the final result. If I'm assuming this C parameter to be 100 times smaller than the standard model prediction, then we have parameter space as low as 10 to the 8 GeV or 10 to the 10 GeV, depending on what C you take. And in the paper, we just assume that there's an additional scalar that couples to the Higgs, and that triggers the electroweak phase transition at a temperature about 10 times bigger than the prediction of the standard model. Okay, so at this stage, then you may say that there's some difficulty with the consideration. But it turns out that if you're including something also unexplained in the standard model, which is the neutrino mass. If neutrinos are Majorana, then this dimension 5 operator must exist. This is the one-bar operator involving the 2 leptons and 2 Higgs. And the scale is the neutrino mass divided by the electroweak VEF. If I'm considering this operator in the picture, in what we have talked about so far, it turns out that everything can be consistent. So the idea is that this operator violates the lepton number. So the transfer route is not expanded. So now we're still, again still starting from a non-zero angular momentum. So I'm going to estimate how big the baryon symmetry is if I have this lepton number violating operator. So the diagram looks a little bit more complicated, but the idea is still the same, that you have the PQ asymmetry, strong sphaleron converting it into the quark carrier symmetry. And then in the standard model, you have Yukawa coupling and electroweak electroweak sphaleron processes. This quark carrier symmetry will be reprocessed into the Higgs number asymmetry and the lepton number asymmetry that you referred to earlier. And these asymmetries, importantly, would now become the lepton number, the lepton asymmetry by this one-pair operator. More technically speaking, what we're producing is not the lepton number, but the B minus L. And this B minus L is non-zero that we're producing, and this can occur at a very high temperature. And this B minus L is conserved even after the electroweak sphaleron process, meaning that I can produce this B minus L at a very high temperature, and I just keep it there. And eventually going through the electroweak phase transition, this B minus L is unchanged. It is conserved by the electroweak processes. So in that case, then the estimate of the abundance would be that we still have the usual, let's see. Yeah, for example, if you focus on this part, the number density for the B minus L is again proportional to theta dot times T squared that we have seen before. But the main difference is that now I don't have to evaluate this expression at the electroweak phase transition temperature. I can evaluate this at whatever the peak production is during the evolution, because I'm producing this B minus L high temperature and it is preserved until today. What happens at the electroweak phase transition? Yes.
Raymond, I'm sorry, but when you're talking about this Majorana mass, it is a physical mass of measurable neutrino, or it is a higher mass, I mean, some kind of, you know, those neutrino which we do not see. Which mass it operates with?
Yeah, so this is the physical neutrino mass, the neutrino in the center model. The three species.
So the one which is very small, you mean, right?
Yeah, that's right, like 0.1 electron volts.
Okay, thank you.
Yeah, yeah. So that means we have no free parameter in this consideration. So instead, we're just saying that now we have something we could expect in the standard model, and that would change the estimate of the baryon symmetry. And the idea here is that we're producing B minus L, and that gets conserved even after electroweak phase transition. So even though we have almost the same expression as before, but the temperature is not evaluated at TEW, but at any and at whatever temperature that gives you the biggest production of B minus L. And the additional ratio here does the rate of this process of the lepton number violating process, which is given by this formula. This is the coefficient you saw before squared. To make the dimension correct is T cubed. And this fraction gamma over H tells you that if gamma is smaller than H, it doesn't mean that we're not producing B minus L. It just means that we're producing it in a freezing picture. We never reach equilibrium, but we're still producing it, even though it is under thermal abundance. So this is the suppression. You can think of it as the freezing suppression if gamma is less than H. And with all this taken into account, you can see, for example, that when the temperature is less than 10 to the 12 GeV for this neutrino mass, then this operator, gamma L, would be out of equilibrium. But again, we have the freezing production. And let me go more quickly in the evaluation. So this...
Sorry to interrupt. Just a question before, when you introduced the Weinberg operator, for your scenario to work, do you have any constraint on what the heavy partner's mass should be? Like, it should be heavy enough? Or...
So yeah, so it has to be heavy enough so that this effective operator is sensible, meaning that whatever temperature we're considering, we're assuming that the right-handed neutrinos are heavier than that temperature. And the temperature we're considering are not high. For example, it can be 10 to the 10 GeV. So it's easily compatible with the seesaw mechanism.
So
we also
large Ikawas, I guess is what you're saying.
Yeah, yeah. But we also don't need to have the right-handed neutrino. We can just have this seesaw operator. This Weinberg operator there as the effective theory. We don't need to evoke to the seesaw mechanism.
Okay, thank you.
Excuse me, can I also ask a general question about, you are discussing the time evolution. For instance, you always write theta dot, you know, which means the time evolution of the axion field, basically, right? Assuming that it's homogeneous in space. So, but if there is such a boundary condition that theta dot at 0 is something, why it should be homogeneous in space? It can be also axion field at the initial moment might be also x-dependent, and then there will be waves, you know, carrying away the energy.
Or it could be bubbles. I mean, bubbles.
Or bubbles, yeah. It's a particular case of the space dependence. So, so far, nothing was said about this.
Yeah, so the reason we don't have any X dependence in the field is because we're having an initial field value during inflation. So inflation would just make the field homogeneous over the horizon. So we're thinking about the zero momentum condensate of the PQ breaking field during inflation.
Okay.
Yeah, so so whatever fluctuation you have would be inflated to larger than horizon.
Okay.
Yeah. Okay, so what I want to quickly go over here is that this is the formula for the B minus L yield, and this is the formula that we motivate. The question is, where do we evaluate this expression? Then it depends on the cosmological evolution. Let's take a radiation-dominated era. Then gamma over H will be proportional to temperature. Theta dot is just theta dot. Entropy density is T cubed. So this is theta dot over T. And as we say before, theta dot itself has different evolutions depending on different potentials, and also depending on where the radial mode is. So now you can see different combinations that you could have UV dominated or constant or IR dominated. So it really depends on where you are in the cosmological evolution and what potential you assume and what kind of background cosmology that you assume. And this is carefully done in our paper called Lepto-Axiogenesis. And you will see, if you open it, you will see that it's a 72-page paper. And not because the mechanism is complicated, it's only because this evaluation is complicated in the evolution of the cosmology. You have to go through many different cosmological eras and look for the peak production and make sure that everything else is consistent and so on. Okay, so here, let me just show you the final plots. So the first case is radiation-dominated universe, assuming quadratic potential. In that case, then, for example, everywhere in this region of the white parameter space, we have consistent story for the baryon asymmetry. But above the dashed line, the dark matter abundance coming from kinetic misalignment mechanism overproduces dark matter. But that also means that if you're living exactly on the line, then not only are you explaining the baryon symmetry, but also the dark matter abundance. And as you can see, we would require the decay constant small again, 10 to the 8 to, for example, 10 to the 10 GeV for the neutrino mass that I'm taking up here. And this SI is the initial field value of the axion, which is taken to be 10 to the 16 GeV or so. And the contours in the blue line show you the required mass of the axion, which is around 30 TeV to 50 TeV in this choice of parameters. For different choice of parameters, for a smaller neutrino mass, in that case, then the axion mass has to be heavier, hundreds of TeV. But again, you have consistent cosmology for reasonable choice of parameters. And in the other case, in the matter-dominated universe, instead of radiation-dominated, in this case, it turns out that the formula actually predicts a specific axion mass, or the soft mass of supersymmetry breaking. And it is not a parameter, we didn't choose it, it is predicted from the baryon symmetry. It has to be around 700 TeV or 10 to the 4 TeV, depending on your choice of the neutrino mass squared. And in here, the white parameter space explains baryon symmetry. In this region, not on the line, but in this region, dark matter is also explained if you choose the corresponding thermalization temperature of the radial mode of 10 to the 7 GeV or 10 to the 8 GeV. And for example, here, this corner explains dark matter abundance as well. But outside the corner, you only explain baryon and you underproduce dark matter. So it turns
Raymond,
out that, yes.
sorry, in this plot, you've got n equals 10, n equals 12, that's the quality.
Exactly, that's the dimension operator that we need to have to ensure the quality of the.
So for the dark matter, what's the n there? Is it still?
So to the left of this line, n equal to 10 is already sufficient. So, and this is not linear, so you cannot say this is 12, this is 10. Okay. 8 does not live here. Yeah, I don't know. Okay. It would be somewhere here, but it is close to 9 to 10.
Okay.
Yeah, it has to be high enough dimension operator to preserve the solution.
And you actually using your baryogenesis mechanism answer the question whether theta dot has to be positive or negative?
Oh, no, because
Why
I don't. Because I don't think. Oh wait. Oh.
You should be able to.
Oh, you mean assuming that we're living in the universe where we have more baryon than antibaryon, then yes.
That's the last time I checked, yes.
Yeah, so that's the theta dot, yes. Then it would have to be.
So which one, so which sign is this, positive or negative?
So it also depends on what this coefficient is. As you have seen before, in the case of CB, the two contributions are opposite in sign. So you cannot fix it until you have a concrete model. For example, if you look at this. If I set CW to 0, then CB is positive. Then in that case, because our YB is positive, then theta dot has to be positive.
Good.
Yeah. But if CW is bigger than some number and turns it negative, then theta dot has to become negative.
Okay.
Yeah, same story with this B minus L coefficient, the C coefficient. Yeah, and we do have explicit formulas in the paper about the C minus L, CB minus L. Okay, so that comes to the conclusion. So I hope to convince you that Lepto-Axiogenesis, which is a combination of kinetic misalignment mechanism and axiogenesis with the Weinberg operator, allows us to use the QCD Axion to simultaneously address 3 mysteries of the universe. So that's what we're very excited about. And the possible signatures include, for example, we say the QCD Axion searches with small decay constant. And I don't have time to talk about it, but we also need to require the Saxion-Higgs mixing to thermalize the Saxion, as we discussed. And this enhances the thermalization rate, and that allows us to be in a parameter space that we saw before. And this can lead to signatures in the collider. And the last thing, that's about parameter resonance that I did not have time to talk about. So I will leave it here. Thanks a lot.
Thank you, Raymond. We'll have some virtual applause here. Not sure how to do that, but you can applaud if you want. Any questions? We had a lot of questions during the talk, but if anyone else has questions still.
So basically, the mass of this Saxion, the smallest it could be was, I thought I caught it was 40 TeV. Is that what it was?
Yeah, so around 30
oh, 30.
TeV.
So this, earlier in the talk, you mentioned a GeV Saxion, but that doesn't survive in this version.
Yeah, for Lepto-Axiogenesis, yeah, it has to be heavier than GeV. Yes.
I see.
Yeah, but for axiogenesis, it can be as light as GeV or even lighter. Yeah, let me go back to the axiogenesis. No, this is kinetic misalignment. This one. So this is the Saxion mass. So it can be GeV. Yeah, but here, just as a reminder, you need to raise the electroweak phase transition temperature. Yeah.
But for this mixing with the Higgs, I was just trying to see how strong the mixing is, how light this Saxion could be to give corrections to the Higgs that you might be able to see at the LHC.
Yeah, so that's possible. So let me see. Yeah, I don't have it in any of these plots, but in the paper I had with Keith a few months ago, we considered the Saxion, for example, as light as tens or hundreds of mega electron volts, and there's a mixing between the Saxion and the Higgs in order for us to thermalize the Saxion successfully. And in that case, it would be probed by the experiment called Clever. So it is possible that the Saxion-Higgs mixing could lead to signatures in the collider, but not in the entire parameter space in this talk.
Mm-hmm.
Yeah.
I had a question on your neutrino mass connection. If I do invoke some heavy neutrinos and imagine that I have some type of leptogenesis happening, how does this interfere with your setup? Is it even possible to do that?
Yeah, so let me think. For example, normally I would think it would be one or the other scenario, because for leptogenesis, you need to put the heavy neutrinos in thermal equilibrium. I guess both can still happen at the same time. So if the temperature is higher than the right-handed neutrinos, then you can put them in thermal equilibrium and go through the leptogenesis story. But at the same time, you may also have the production from Lepto-Axiogenesis. So I don't think there is an interference. I mean, when I say that, I assume the right-hand neutrino to be heavy enough so that I can use this effective operator. It is just to be consistent with the analysis that we did in the paper. But it's not necessary for the mechanism to work, because instead of having this diagram with a dimension 5 operator, I should have considered the scattering with, for example, the right-hand neutrino in the bath and the lepton number, Higgs number, and everything in the bath. So it's just a different analysis to consider. So yeah, I don't think it is in conflict with light neutrinos in the thermal bath. But
I guess it's also a model-dependent question.
Yeah. So to see if you want to drop lepto-axiogenesis and only keep kinetic misalignment contribution to dark matter with leptogenesis, yeah, I think the answer depends on the model.
Okay.
Yeah, and if we have one more minute, I just want to show a very quick plot. So I didn't have any time to talk about the axon-like particle in our discussion today, but if we do, then this is the prediction that we're making. It's pretty striking. So this is the axon parameter space with the coupling with the photons, and this is the QCD axion, the conventional misalignment mechanism. And if you want to produce both the baryon symmetry and dark matter from an axon-like particle, not the QCD axion, then you have to live in this green band. It turns out to be much more accessible than other conventional predictions to the experiments.
All right, very interesting. Do we have any other questions? If not, we'll thank Raymond again.
All right, thanks.
Yeah, so thank you, Raymond. Yeah.
All right, thanks guys.
Stop recording.